Ever since Amazon acquired Whole Foods, they've been exploiting their technology to gain an unfair advantage over local farmers. Organic foods shipped all the way from countries like China are being sold by Whole Foods rather than that from local farmers, which results in consumers having to pay a really high price for produce, high rates of pollution due to transportation, increasing city gridlock problems, and most of all, our local farmers being financially burdened due to their minuscule purchased amounts of produce. However, we plan to solve this problem by providing farmers with an easy-to-use platform to reach their consumers. Introducing Local Foods for One Hacks, a simple service that allows farmers to post their items on their personal website. First, the user is prompted to log in using their Local Foods account. Then the user send an email verification code. This is achieved using Twilio SendGrid. If the user is new, their data is then stored on CockroachDB. Before adding an item to his or her store, the farmer can diagnose a fruit or vegetable for diseases. The farmer can also add an item, such as a fruit or vegetable, to his or her store. As you can see, the vegetable is classified and the disease is classified. Since the potato was classified as healthy, it is now listed on the farmer's store for consumers to buy. Moving on to how we trained our machine learning model and built our neural network from scratch.
So we have two models for this project, and we get the data sources for the training data from Kaggle. And on the right, we can see a word cloud of the possible types of diseases that the leaf might have. And on the left, we see the amount of training samples we have for each one of these, and we have roughly 1,500 to 1,000 for each one of these diseases. On the left, we can see that the proportion of the training samples to the total are roughly the same. And this shows that the training won't be skewed. On the right, we have images of the leaves and the diseases they might have or they're healthy, and they're included in the title. We can see the types of fruits we have, and on the bottom we have the augmented version of the top fruits. And we use these augmented versions to expand the amount of training samples we have, so we have more training samples for our model. This is a key aspect of our project, as we only have 107,000 parameters, and most models have over 60 million parameters for such a complex task. And we use the SqueezeNet outlined by the Berkeley paper. And the FIRE module is found in the SqueezeNet, where we squeeze and expand our representation. We squeeze the representation of the image, and we expand it out using 1x1 and 3x3 convolution filters. And you can see the model architecture. We're squeezing and we're expanding it out, and we're concatenating that output, and we're pooling that. And on the right, we see an image of the TensorBoard graph. And I use TensorBoard a lot through this project to debug my TensorFlow model, especially as I was running through many problems, especially since the amount of parameters were very low, and I had to experiment with many different types of optimizers. And I finally came up with RMSProp to quickly get to the saddle point of a loss function, like the global minimum of a loss function. And on the right over here, we have a piece of code. So there wasn't any implementation that the paper gave, so I had to use the paper and the TensorFlow API to create code to implement this model. So there's something called the FIRE module that outlined the paper. And as I said, there's a squeeze and expand. So I have a method for both of them. And we're expanding, we're squeezing, and we're expanding that out, and we're concatenating that input. And we can see a convolution, the pooling, and then the FIRE modules to create our model. So this is a picture of our model results on a couple images. The green ones are the ones that the model detected accurately, and the red ones are the ones that they did not detect accurately. All of this code is generated through the Colab notebook that's on DevPost. So if you want, you could run the code again. You can see the display. The code for all of these displays are included in this Colab repository, and the last image was created on this code block. And if the prediction is equal to the actual label, we would keep the colors green, otherwise we'd keep it as color red.